Hey guys, so today I'm going to be going over the right hand rule for you, but before I get into that, let's first establish a convention. And that convention is that when I draw a dot, that means that current is going out of a page, and when I draw an X, that means current is going into the page. And the reason for that is because if I have an arrow, and that arrow is going to have feathers on the end of it, and it's going to need a head. If I'm looking at it from this angle, I see an X because of the feathers, but if I'm looking at it from this angle, I see a dot. And so looking at that, right, because there's going to be feathers along here, and then some feathers down there with the arrowhead, and so that's going to look like an X, whereas in this one, and these arrows in this situation are at an angle, I've just drawn it to show you, the arrowhead is going to just make a dot. And so with that convention established, let's now get on to the actual right-hand rules. So the first one is the wire rule. And the wire rule states that for a current flowing through a wire, there is a magnetic field generated as perpendicular to that wire. And so what that looks like, if the current is flowing towards the top of the page, then there's going to be a magnetic field generated like this, going around the other side of the page. And so the way that we can figure that out is, let's say we have a hand, and then take your hand, put it around a pencil, like so, and then what you'll see is that your fingers trace the path of the magnetic field here, and your thumb indicates the direction of current right here. And so try that out with a pencil, and you can see that will work. It's important to always use your right hand, because that's the right hand rule. The next thing that we need to know is for solenoids. So let's say you have current coming in this way through the solenoid. That means it's going to go all the way around, continue along, and then eventually come out this side. I'll just get rid of those dots because we don't need them anymore. And so then the thing that we can do with this guy is, instead of using our thumb for the current direction, we're now going to use our fingers for the current direction. So we're going to have our thumb sticking up, and then our fingers in the direction of current that's coming around here with the coils. And that means that our current direction is this way across the coils, and our magnetic field direction is pointed by the thumb. So that's the solenoid rule. The next rule that we need to know is usually for particles, though sometimes we use it to figure out the force on objects. And with that one, what you need to know is the direction of motion of the particle. And this is for positively charged particles, because let's say you have an electron which is negatively charged, and it's moving this way. What's going to end up happening is that electron is actually going to move to the side. And when it moves over there, it's going to leave an absence of negative charge, right? And you can think of an absence of negative charge as positive, because compared to this location, the location where the electron was before is actually going to be more positive than over here. So if you have a negative charged particle, you can reverse the flow to say that this would be the positive flow, which is what we need to use, and this would be the negative flow. So this is the motion for positive particles. And then the other thing that we need to know is the direction of an external magnetic field. And that external magnetic field is going to exert a magnetic force on a particle. And it's important to note that this is an external magnetic field because a charged particle will produce its own magnetic field when in movement, but that magnetic field, usually in comparison to this external magnetic field here, will be so small that it will be negligible. Okay, so let's now review everything that we've gone over. So we have the wire rule, the solenoid rule, the particle rule, and we know that this needs to be the direction for positive charges. And further, we also know that a magnetic field will produce the movement of charged particles, or you can also say that moving charged particles, which is just another way of saying current, is going to generate a magnetic field. So these two are codependent. One causes the other, and the other causes the one. But before we get into any questions, I just want to go through some pictures of hands demonstrating the right hand rule so you guys know how your hand should look when doing this. But keep in mind that this isn't every hand position out there for the right hand rule. It's just a few situations of it. So the first one is what I call the punch of power position, which is pretty much just for the wire rule and solenoids. And so here you can see that this is the wire would be somewhere in between there. And in this situation, current is flowing this way. And in this situation, current is flowing upwards. And then the magnetic field in the bottom image here would be wrapping around like so. So it would be coming from the back and then going over towards the front if I was to draw it with dashed lines. And then in this case, it's coming around the back and then going towards the front. And so that's for our just okay punch, or punch of power as I like to call it. And then the next one we have is our karate chop. And so with the karate chop, that's for the particle rule as I called it. And so here you can see a few instances of it. And so the first one here, the force is coming out of the palm. The fingers are indicating the direction of the magnetic field. And the thumb is indicating the motion of a positive particle. It's also important to keep in mind that this is for the right hand, so these are all pictures of right hand. And in our second image down here, the force would actually be going somewhat at an angle there, which is totally fine. Nothing is prohibiting that. The magnetic field would be coming also at an angle there, going this way. And then the thumb would be indicating the direction of motion as this way, where if you were to look at the thumb head on, this would be just a dot for the motion. But because we're kind of at an angle here, that's why I've drawn it. But otherwise, it would be more of a dot coming out of the page at you. And so that is our hand positions. Let's try some problems. Okay, first question. A uniform magnetic field is directed into the page. A charged particle moving in the plane of the page follows a clockwise spiral of decreasing radius as shown. Using the formula, R is equal to mv over bq, a reasonable explanation is. From our answers, we can see that we need to determine the charge sign and whether it's slowing down or speeding up. So first, let's determine whether it's slowing down or speeding up. If we have the formula, R is equal to mv over bq, we know that m isn't changing, b isn't changing, and q isn't changing. The only thing that's possibly changing is r and v from the question. So what we can really say is that r is directly proportional to v. And that's because these three variables aren't going to change. So let's just assume that they're 1 for this instance, and then we can get this equation. So proportional just means that an increase in one results in an increase in the other. So conversely, if the radius decreases, the velocity, or the speed, will also decrease. So therefore, we know that the charged particle should be slowing down. So we can cancel out these two options. And also, it could be none of the options beside here, but let's see if it is one of these options first. When something's directed into the page, we use an X. So take your fingers now and point them into the screen. Now, point them approximately above the yellow dot. And now we know that the yellow dot is traveling in a circle. And if it's traveling in a circle, that must mean that the force is applied inward. Because if the force was applied outward, the charged particle would be spiraling this way. This is from circular motion. And so the force is applied inward. Since we know that the force is applied inward, our palm, your fingers should still be pointing into the screen now, your palm should be directed inward. This means that your thumb should be directed this way. However, we know that our particle rather, is traveling in this direction. Because our thumb and the direction of motion are opposite, this goes back to what I was talking about with electrons, because we're moving in the direction opposite to the motion of positive charge. So that means that our charge must be negative and slowing down. So answer B is correct. A current runs through a horizontally oriented wire toward the right of the screen. What type of field is generated, and what is the direction of B as viewed from the left-hand side of the wire? Okay, so first, I would really recommend taking out your pencil and pretending that it's a wire. For our purposes, because I can draw it on a nice board, I'm also going to just draw a wire around this pencil. Great. So now we know that a current runs through a horizontally oriented wire, and that current is traveling to the right of the screen, so over here. And then we want to find out what type of field is generated by this current and what direction is it heading in, viewed from the left-hand side. So that's going to be from this side, if we're looking at it. So take your finger, or your hand rather, and point your thumb in the direction of the wire. This is your wire rule. Then your fingers are going to naturally curl this way because you're using your right hand. So that means that because we're using our wire rule, our fingers, except for our thumb, which points in the direction of current, our fingers are pointing in the direction of the magnetic field, which is this way. And so that means that if I was going to draw a circle, that the current is going to be flowing in this direction, which, if you imagine a clock hand, right, where this is 12, this is 1, this is 2, and clocks move this way, that's going to be clockwise and a magnetic field. And the reason why we know it's not a gravitational field is because current doesn't produce a gravitational field, because charged particles have such a low mass compared to the mass of the rod. So the movement of electrons itself isn't going to be generating any gravitational field. So you should know additionally that it's not D&E right off the bat. Okay, let's move on to a different question. Label the magnetic field produced by the current carrying loop at the top, bottom, and opposite sides of the loop. Okay, so thinking about this, if we have a hand, right? And we point using our wire rule, our thumb in the direction of the flow of current. That means that our regular fingers are now showing the magnetic field. So here, the magnetic field is coming out of the page, and on this side, it's going into the page. Now, if I move my hand around this way, and then I'm going to need to rotate it, apparently around a really wide angle, to accommodate for the new current direction, which is going to be this way. Now, my hand is pointing in this direction, my fingers rather. And so the current's coming out on this side of the ring and going in on this side. If I continue moving my hand around, you'll find the same thing. Current coming out of this side and going in to this side. And I'll just move my hand around quickly, or rather, actually, I'll just draw it in that position here. So there's my thumb and my fingers, and here's my thumb, and here's my fingers. Okay, so let's move on to the next question. Question 4. A rod is placed lengthwise, horizontally, on a frictionless table permeated by a magnetic field directed upwards, with an electron flow towards the north. What direction does the rod move in? Okay, so first, let's just establish how I'm going to look at this problem. Because in these types of problems, I find it always useful to say what frame of reference we're going to be looking at the problem from. So for this one, I'm going to choose the bird's eye view. Other things that you could have done is view it from the side, like over here, or from behind, over here, or from in front. But I'm going to choose the bird's eye view because I think it best suits this scenario. This is something that you'll have to develop when working through physics problems. How do you want to look at the question? And you know that this frictionless table is permeated by a magnetic field exactly upwards. So now I'm going to draw my bird's eye view, which is this view. So first, I'll draw a table. Let's say this is my table. Next, I'm going to draw the rod on my table. So that's going to look something like this, right? And there's electron flow towards the north. So here, I'll draw my electrons flowing upwards because I'm treating this as the north, this direction. And then they're asking me what direction does the rod move in? Well, to move, the rod has to be experiencing a force. And we've said that the table is frictionless. So the only other force that's acting, other than gravity, is going to be a magnetic force because there's also a magnetic field present throughout this whole table. And because it says which direction does the rod move in, we can assume that the magnetic force applied on the rod is greater than the gravitational force. So thinking about this, first, put your hand facing towards you, that is out of the screen, your fingers. And now your thumb may be pointing in the direction of the electron flow. But remember that we don't consider electron flow. We consider the movement of positive charge. And so if electrons are flowing that way, our positive charge must be flowing the other way. So this is the movement of positive charge. So your thumb should then be directed down towards the south direction. And because your fingers are pointed away from the screen, that means that your palm should be facing this direction.
That's the direction that the force is pointing in, which means that is the direction the wire will move in. And so I hope this video helped you, and good luck!